Hello everyone, my name is Liang Wang and I'm the corresponding author of the study Application of Machine Learning Algorithms in the Analysis of Search Spectra for Rapid Discrimination of Shigella SPP and E. coli. Today, I'm going to introduce the study to you, and if you are interested in the study or have any questions about it, please do not hesitate to contact me via my email shared in this poster. Thank you for your attention in advance. Shigella and the enterotoxigenic E. coli are major bacterial pathogens of diarrheal diseases. That is the second leading cause of childhood mortality globally. Currently, it's well known that Shigella species and E. coli are very closely related with many common characteristics. Evolutionarily speaking, Shigella species are positioned within the phylogenetic tree of E. coli. Therefore, discrimination of Shigella species from E. coli is very difficult. Many methods have been developed with the aim of differentiating the two species, which include but are not limited to biochemical tests, nucleic acid amplification and mass spectrometry, etc. However, these methods suffer from high false positive rates and complicated operation procedures, which requires the development of novel methods for accurate and rapid discrimination of Shigella species and E. coli. As a low-cost and non-invasive method, surface-enhanced Raman spectrometry is currently under intensive study for its diagnostic potential in bacterial pathogens, which is worthy of further investigation for its application in bacterial discrimination. In this study, we focused on clinically isolated E. coli strains and Shigella species, based on which search spectra were generated and characteristic peaks for Shigella species and E. coli were identified, revealing unique molecular components in the two bacterial groups. Furthermore, comparative analysis of a machine learning algorithm showed that the CNN algorithm achieved the best performance and robustness in bacterial discrimination capacity when compared with random forest and support vector machine algorithms. Taken together, this study confirmed that search paired with machine learning could achieve high accuracy in discriminating Shigella species from E. coli, which facilitated its application potential for diarrhea prevention and control in clinical settings. For graphical summary of the study, please refer to Figure 1. In particular, I'm going to introduce the study by dividing it into two sections. First of all, average search spectral and Raman barcodes generated through deconvolution analysis in Figure 2 greatly supported the electronic storage of search spectrum, converted molecular characteristics into information, and improved the recognition of bacterial species. Secondly, in this study, we applied the two algorithms, TSNE and OPSDA, for the cluster analysis of Shigella species and E. coli search spectra in Figure 3. During the application of TSNE method in search spectrum, the result showed that two bacterial genera could be well separated into two groups, but the classification boundary is not clear due to the mixture of certain number of E. coli search spectra. As for OPSDA, it's a multivariate statistical method for supervised data clustering, which provides insights into the divisions of data groups based on high-dimensional spectral measurements. When using OPSDA method for analyzing the same data set, it was found that Shigella and E. coli spectra were well clustered into two groups with smaller intragenous variations, and the boundary between the two genera was clear. Thirdly, ROC curve aims to compare the sensitivity and specificity across a range of values for the predictability of supervised machine learning methods, and AUC means overall accuracies in discriminating data samples. As for confusion matrix, it's a table that shows the classification results based on the true class and predicted class. Therefore, in this study, we plotted both ROC curve and confusion matrix for the optimal prediction model CNN. As for the ROC curve, the x-axis represents the specificity, while the y-axis represents the sensitivity. It could be seen in Figure 4 that the AUC value was 1, which indicated that the CNN model had a better high specificity and sensitivity. The confusion matrix showed the specific performance of the model on the test dataset. It could be seen that the prediction accuracy of CNN model was 100% for Shigella and 99% for E. coli, while 1% of the E. coli spectrum was misidentified as Shigella, indicating that this spectra could be accurately assigned to the correct species with very low error rate. Finally, we schematically illustrated the computational mechanism behind the CNN model classification of Shigella species and E. coli search spectra in Figure 5. It could be seen that the heat map distribution of the raw spectral data was determined by the intensity of characteristic peaks, that is, high intensity region appeared in red and the low intensity region appeared in white. As for the spectral data output by the CNN model, they were not classified according to the characteristic peaks as previously inferred. Instead, according to the results, there are obvious differences in the weight distribution between the spectra of the two bacteria genera. To further demonstrate how the CNN model classified Shigella and E. coli, we used TSNE to show the extraction results of spectral features by the model. It could be seen that the two bacterial groups were divided into two well-separated clusters, and according to the label display, it can be judged that the model can distinguish the two bacteria well. Taken together, this study confirmed the application potential of this technique while handheld Raman spectrometer in the discrimination of Shigella species and E. coli, which may facilitate diagnosis, control, and prevention of diarrhea in clinical laboratory in near future.